Hi everyone, my name is Linjiao, and today I'm happy to talk about our work on using ML prediction APIs in a more accurate and cheap way. This is a joint work with Professors Matilda Hari and James Stowe. Today's talk is divided into three main components. First, we will give an introduction to machine learning as a service. And next, we will talk about our proposed solution, FrugalML, which talks about how to save up to 90% of the cost while using those machine learning APIs. We will go over the main idea behind this framework, how to use it, as well as the program evaluation on some real-world machine learning APIs. And finally, we will draw conclusions and talk about what is next. So first of all, what is machine learning as a service? For the past few years, people have already observed a big success of machine learning in many domains and want to extend that to many other domains. But people in other domains may not always be the machine learning expert, and therefore we want to help those people to benefit from the machine learning breakthroughs without worrying about the low-level overheads, such as model training, data labeling, etc. Nowadays, there are many participators in this market, such as Google, Microsoft, Amazon, IBM, and many other companies. According to the market research company Model Intelligence, the market size of machine learning as a service was already $1.0 billion in 2019 and expected to reach more than $8 billion in the next 5 years. Here is an example of machine learning as a service. Suppose one wants to do a facial emotion recognition task. Then instead of hiring his or her own ML expert and building his or her own ML model to do this task, you can basically call the Google Vision API, and the process is very simple. You just upload this image to this machine learning vision API, and the API returns the emotions as well as a confidence score. For instance, here, this Google Vision API gives the label happy or joy of this image with a pretty high confidence score. The cost is pretty tiny. It's only about $0.0015 per image. So far so good, right? But what is the problem? There are many commercial APIs with the same functionality. For instance, for this facial emotion recognition task, Google, Microsoft, Amazon, and many other companies all provide the same kind of a functionality for this particular task. But there is a big difference in their performance and cost. Therefore, a natural question is, which API or combinations of API to use? To address this problem, we propose a solution called FrugalML, which essentially optimizes for the best sequential strategy within a budget constraint. Across all the tasks and data sets we evaluate, we observe up to 90% cost savings or 5% better accuracy with the same cost. How does FrugalML work? It works as follows. First, it calls a base service. Say it's a GitHub model, and then it takes the predicted quality score and label from the base service as a feature to decide if the prediction is already acceptable or if an additional API should be invoked and which one should be invoked. Take this figure as one example. Suppose we're doing a facial emotion recognition task. We get a facial image X and we send it to GitHub model first. If the prediction is happy with quality score less than 0.9 or surprise with quality score less than 0.6, then we send this image again to a Google API to get a better prediction. Or if the prediction is sad and quality score less than 0.8, or if it's anger with quality score less than 0.7, we pass the image to the Microsoft API to get a better prediction. Otherwise, we believe this GitHub model already gives a good prediction and simply accept it. To the real users, those things are essentially a black box. Then how should a user actually use this in practice? Actually, the usage of FrugalML would be very similar to the usage of a real commercial API. Let's take face detection as one example. If you want to use the Google API for face detection, you basically invoke a Google client and then call the function face detection on a particular image, and then that's it. For FrugalML, during this deploying phase, it's almost the same. You invoke a FrugalML strategy and then call the face detection function to get response. The only difference is that FrugalML requires an additional training process where you can set up your own budget requirement and ask FrugalML to find the best strategy for you. Notice that this training phase is essentially offline. So how do we actually train a good FrugalML strategy? Notice that there are many parameters in a strategy. For instance, how to pick the right or optimal base service, how to pick the right or optimal add-on services, how do you set up the switchers, and etc. This is modeled as a combinatorial optimization problem. And the interesting question is, how do we develop a provably efficient solver? This involves statistical efficiency, meaning that we want to use as few samples as possible, and also computational efficiency, meaning that we don't want to take a super long time to finish the training process. To tackle the problem, we observe a nature-specific structure within the optimal coding strategy. And based on that observation, we're able to develop an approximation, a solver that gives a 1/n accuracy loss compared to the best strategy. So here n is the number of samples we need from the APIs, meaning that we want to annotate those n samples from each of the APIs. The computational cost of this approximation solver is proved to be linear in n from relatively large n. So how does FrugalML actually work in practice? This figure gives a case study on a facial emotion recognition dataset, FER+. Here we set the budget to be $5, which is the same as the cheapest commercial API. As you can see from this learned FrugalML strategy, for more than 50% of the time, we would only require to call the GitHub model. And that's probably why FrugalML could save the budget. And second, we do use different quality score for different facial emotions. And that tells us the importance of this label-dependent quality score. How does this actually perform? Right? What is the performance metric? So this figure gives the accuracy and cost comparison across different ML APIs as well as FrugalML. So first, we notice that the cost of FrugalML is the same as the cost of Face++, which verifies that our budget requirement is satisfied. Second, notice that Google API's cost is actually higher than any other individual APIs. However, its accuracy is lower than Microsoft's accuracy. This essentially tells us that higher cost does not always imply higher accuracy. Therefore, it's very important to decide which API to use, even for the users with high budget. Perhaps most surprisingly, while FrugalML incurs a relatively small cost, its accuracy is even better than the best commercial API, Microsoft. This is probably because FrugalML, to some extent, could be viewed as an ensemble of all the individual APIs. Therefore, It uses the information from all the individual APIs and should be better than any individual of them. Now let's zoom out a little bit and try to understand what is the accuracy and budget trade-offs achieved by FrugalML. So from this figure, we can first notice that compared to any individual API, FrugalML enables the user to select their own budget or their own accuracy requirement. This gives a large flexibility compared to individual APIs. Second, to match the best commercial APIs accuracy, say Microsoft API's accuracy, FrugalML requires only 30% cost and therefore could save you quite a bit of money. Also, if you do allow FrugalML to use a relatively large budget, then its accuracy could be higher than the best commercial API. We also compare FrugalML with a simple cascade approach, which is a red line in this curve. As you can see, across different budget requirements, FrugalML, which is a blue line, consistently outperforms the simple cascade approach. So does FrugalML only works for facial emotion recognition? Of course not. So here we study FrugalML's performance across 12 different data sets for 3 different tasks, including facial emotion recognition, sentiment analysis, and speech recognition. This figure shows the cost savings achieved by FrugalML while match the best commercial API's accuracy. As you can see here, typically, FrugalML could achieve more than 50% cost savings, and sometimes up to 90%. This figure shows FrugalML's accuracy improvement while match the best commercial API's cost. In fact, FrugalML could reach as high as 5% accuracy improvement. So this shows FrugalML's other benefit, which is utilizing the power of all APIs in the market can actually lead to overall higher accuracy. So let's look at what we have already looked at. In this work, we essentially try to study how to best use machine learning APIs in the marketplace within a budget constraint. Towards this problem, we propose a solution called FrugalML, which gives provably performance and efficiency guarantee. Empirically, we notice up to 9% cost savings or 5% better accuracy with the same cost. To stimulate more research in this area, we also released the dataset with more than 600,000 samples annotated by those machine learning APIs, as well as our code. Is this the end of the story? No. In fact, this is a really underexplored area, and there are many open problems here. For instance, in this work, we focus on the simple classification task. But there are many machine learning APIs focusing on the more complicated tasks. For example, the segmentation task in computer vision or the language translation task in the NLP processing. How can we actually allow FrugalML to work for those more complicated tasks? In addition, in this work, we assume that all those APIs, they remain stable. However, in practice, many APIs could have frequent update. So then their performance may not be stable. Then how can we detect such a performance shift and adjust our ML API calling strategy to take that into account? That also remains open. And finally, in this work, we focus on accuracy and cost, which are important metrics for the users. But there are also other metrics, for instance, fairness metric or latency requirement. How could one take into account all those different metrics and build a holistic approach? That also remains open. In fact, there are many interesting open problems in this domain, and we're really excited about keeping working on this exciting area. Cool. Thanks for your attention. Our code and data are already available in this GitHub repository. If you're interested in more about the theoretical analysis and the empirical results, feel free to visit our project website and our full paper, or send an email to us. Thank you so much.